Okay, we've done all of part A using conservation of energy. So now going to part B. Part B says, what if... I was wondering where that went. Thank you. I actually went looking for it and couldn't find it. What if we double the length of the nylon rope? Okay, so now we have to think about this. The nylon rope, I said we're treating it just like it's a spring, right?
Mm-hmm.
So if we double the length, it's like we take one spring and then we put a second identical spring. So this would be spring constant K, and this would be spring constant K. And the question is, what is the combined spring constant? Because we have to find that before we can do any more work. So what is the definition of the spring constant? The spring constant is defined by this relationship. Force of the spring is equal to, and I'm just going to put the magnitude, Kx, where x is the amount it's stretched. So what we're going to say is, if I were to replace these two springs with one spring, K, and these, we call them series connections, so I put K sub S. If I were to replace these two springs with one spring, what would happen? How would I find that K? So let's just take, for an example, I put some force F1 here. So it's pulling down with force F1. How much does spring 1 stretch? What's the force going to be on spring 1?
Tension.
Okay, it'll just be the tension, which is F1, right? So for spring 1, we have force 1 is equal to K1 X1. And what about spring 2?
K2 X2 minus X1.
No, spring 2 is still going to have just that same tension on it. And so how much it's going to stretch. I'm only looking at how much it stretches. I'm not worried about what K1 did now. I'm just looking at what happens with K2. And it's going to have the same relationship here, K2X2. And so now the question is, what is the total stretch?
K1X1 plus K2X2.
Well, it'd be X1 plus X2 would be the total stretch. Right. X1 is the amount that spring 1 stretched, and X2 is the amount that spring 2 stretched.
So it'd be KS times X1, X2, X1 plus X2.
Well, that when I go to the green, that is what I'm going to write.
Okay.
But right now, I'm looking at these two springs.
Right.
And so I just say, well, the total amount it stretches is going to be the amount spring 1 stretches plus the amount spring 2 stretches.
Yeah. Okay.
So it's just going to be X1 plus X2. And using the work we've done here, that would be force 1 over K1 plus force 1 over K2.
F2.
No, because it's force 1 is what I put on here. And it's that same force in both cases. So we can actually factor that out. Equals F1 times 1 over K1 plus 1 over K2. That's the total amount it stretches. Now we look at the other one, the equivalent one. Equivalent spring. We're going to have F1. So we're going to put the same force here. You'll have F1 is equal to K series times X total. And so solving this for X total is equal to F1 over K series. And now we can compare the two relationships, and we see that by comparison, we must have 1 over K series is equal to 1 over K1 plus 1 over K2. That is, this is F1 over K series. Well, F1 times 1 over K series. I'm actually going to write it differently so it makes it obvious. So this line here is just taking this equation and solving for X total. And here we had X total was equal to this. So if X total is this and X total is that, if they're equivalent, then we must have these things in parentheses equal each other. So now we can say, aha, if I had exactly the same spring, if I put two of them there, I can have 1 over K series is equal to 1 over K plus 1 over K, which of course is 2 over K. Therefore, K series is K over 2. So the spring constant is cut in half by putting two of them in parallel. Now, all of this work, it was physics. Is it something we've gone over in class?
I think so.
No, we went over the relationship right here. We went over this relationship. And what we were doing here was applying that relationship to a new situation and seeing how it plays out. Because our problem was, what happens if we do this? So I had to say, well, what should happen? Now that we have the K, now we can do all of our work again. We just do exactly the same work we did before, but we replace K with K over 2 because we doubled the spring. So we go up to the beginning and it said, first question, what is the frequency? And the frequency we found was simply, okay, we did a whole bunch of work here to get to the frequency is equal to omega over 2 pi, where omega is square root K over M. So I didn't write the intermediate here, but we could say that frequency is equal to square root of K over M times 1 over 2 pi. Wow, that looks beautiful. And so now we're just going to do that again. We'll have frequency for them in series. It's equal to 1 over 2 pi times the square root of K over 2 divided by M. And you'll get your answer is what this one here was, divided by the square root of 2 because of that 2. Oh, you can't see up there. So when they're in series, so this is for the later part, yeah. It's just going to be the answer we had before divided by square root of 2 because of the 2 right there. So this is finding the actual numbers is anticlimactic because it's just the same calculations you did before. It was making the connection, what happens if you double the spring or double the nylon rope in this case? That's where the actual thought process had to be. Now, the next portion, of course, all of this is the same. So you get down to exactly the same quadratic, except for instead of k, it's k over 2. And so you're going to have just a square root of 2, right? Because all of these have k on bottom. You're just going to have the answer for this is equal to, come on, sometimes it just doesn't like to, square root of 2 times right, so this is going to be our repeat answer. And once again, why is there square root 2 here? I just said this, but I don't want it to be, I didn't quite understand, and I'm not going to ask. Why do I have a square root 2 there?
From k over 2.
I'll give you a clue. I made a mistake. There's no square root. Because in this equation, every k has to be replaced with k over 2. So that puts the 2 on top. So there's going to be a 2 right there. And there's going to be a 2 right there. And, oh, wait, no, I'm wrong. See, that's why I should do things more carefully. Good thing I'm recording this, so everyone can see I was wrong because I was hasty. Why was I wrong? Because this one's not squared. This one's going to have another 2 added on, but that's not squared, so I can't factor it out. So we actually will have to calculate this one out. So I'm going to copy. Oh, that's an M. I'm going to copy this equation and take it down. And then we'll do the calculation with this one. Control, copy. Okay, Brittany, you're shaking your head like I shouldn't have done this. What was the original KS? 1.40. Okay, so there's my new K series. It's that value divided by 2, divided by the M, which was 90 kilograms. That gives us the new frequency. Okay, so there's our frequency using the same equations before, but now plugging in our new K series as 1/2 of the old K. Now for this one here, it's a little more complicated. Mine is, actually, you know what I did before to make my life easier? mg over ks equals, and that's a So here I'm putting the mg over ks since that appears everywhere. And I calculated up here what it was, so I'm just going to take that and multiply by 2. So that's 1.26 times 10 to the minus 1. So that'll make my calculation a little bit simpler. That can't be right. $90 times 9.8 divided by goes around in a circle. I see. Okay. And so, yeah, that times 2. I guess it is. Whoops, 9. Okay, well, I messed that up, but yeah. So that's 0.126 meters. And so our y final S is equal to minus 0.126 meters plus or minus the square root of 0.126 meters quantity squared plus 2 times 0.126 meters times the YA, which was 2.0 meters. And calculate what the square terms. $126. Okay. Or some positive value. I don't really care what the positive value is because we know that you're not going to move up. Yeah, for starting.
Yeah.
Yeah, that's what I did. And so it's going to have to be this one here because you have to go down below. Yeah. You understand what I'm saying? Or do you understand what I'm saying? I'm going to go with that's a no. Okay, so you're bungee jumping. And this is the height where it becomes taut. So you're coming down, you get to this height where it becomes taut, you're not going to then have it stretch and go like this before you stop. Because you would obviously have to stop and change directions to go up. It's going to have to go down before it stops. And so that means my y is going to be negative because I set this as 0 with up as positive. So it's got to go down here, which means you have to have a negative value. And so that's how we do it.
Oh, okay.
Yeah, were you two here when I did the first half of this?
Yeah.
Yeah. Okay. Okay. You want to do another one?
Yes.
All right. What do we want to do? What?
I have what is the maximum velocity?
Okay, so this is
still under 34.
okay, but it's a new situation.
Yes.
Yeah, we're gonna live life on the edge.
Okay. Did you open the other thingy? Okay.
I do have a spreadsheet going, which gives us a way hopefully to back out if it crashes. It very rarely crashes the first time I do it. It's when I do it a second time or a third time when it crashes. Okay, what is the maximum velocity of an 85.0 kilogram person bouncing on a bathroom scale having a force constant of 1.50 times 10 to the 6 newtons per meter if the amplitude of the bounce is 0.200 centimeters? All right, how should we approach this?
Well, I still don't know all the connections between all the equations. So I don't know.
Okay, well, I would start by drawing a picture. And my picture is going to be a cartoon version of it. I'm going to have the person standing on a spring that, of course, is way bigger than the spring in any scale. Why? So I can kind of illustrate what's going to happen. So the person is on this, and they're oscillating up and down. The spring has a spring constant. Actually, I want to change the color there. Spring has a spring constant of K is equal to 1.50 times 10 to the 6th newtons per meter. The person has a mass of 85.0 kilograms. And we have the amplitude of the bounce. What does the amplitude mean?
From the halfway to.
Yes, from the middle point. So
From the origin to not the origin, but that.
So we have the amplitude there and the amplitude there. And this here is the equilibrium spot in the center. And so the amplitude is equal to 0.200 centimeters. So it asks us for that maximum velocity. This is actually one of the homework problems that's due on Wednesday as well.
Oh,
or something very similar to this at the very least. So now we have a picture and we can look at what's going to be involved. So, you said you don't know all of the equations, don't have them memorized. And of course, you don't have to have them memorized. So equations that are involved with these, we had omega square root K over M. We had frequency, well, omega is equal to 2 pi f, so we had period is equal to 1 over f. We had x is equal to amplitude sine of omega t. V is equal to omega a cosine of omega t. Acceleration is equal to minus omega squared a sine of omega t equals minus omega squared x. So we had all of those equations. And those are many more equations that we need than we need to answer part A.
Mm-hmm.
So part A, what's the maximum velocity? Where would you start if I gave you those equations?
So for
we have
angular.
Yeah, we have everything that we need to find angular frequency, so we can use that and plug it in.
Okay, so we find this and we plug it into where?
Oh.
To unit A. Yeah. Second equation.
Mm-hmm.
But we don't know.
This second equation, remember cosine goes between 1 and minus 1. So the second equation tells us that V max is equal to omega A, because cosine can't go bigger than 1. So the maximum that V can go is omega A times 1. Okay, cosine, if I draw a cosine curve,
Yes.
cosine goes like this.
Yes.
Where this is 1, this is minus 1. Cosine goes between 1 and minus 1. And so since cosine goes between 1 and minus 1, if you look in this equation, that cosine in the box, okay, in the box that's going to appear,
Mhm.
can only get as high as 1
Okay.
and as low as minus 1. So that means your speed can only go as high as whatever that box is multiplied by. Since,
Okay, so if it's multiplied by 1, then it would only go up to 1.
well, if omega A is multiplied by 1, then V only goes up to omega A times 1.
Okay.
So that means that your maximum speed must be omega A. So going with what Nye said, we calculate omega, and then we just have to multiply by the amplitude. So I see Nice is already there. What do we have, Nice?
132.
Okay, so 132.84 radians per second. Radians, not meters. So that's our omega. And then how do we find the maximum speed?
Put them back. Second equation.
Omega times 0.02.
Usually we want it in meters per second, so I'm going to multiply it by the amplitude in meters.
0.0.
Okay, did you say that? Okay.
What is T?
That's what he was saying.
You asked what is what?
T.
T? Oh, this goes between minus 1 and plus 1. So since we're looking for maximum, we're just going to take when cosine omega t is equal to 1. T would be 0 if you care, but
That's why I was confused as to why we couldn't put it in here.
yes. So you're not going to be going very fast bouncing on this bathroom scale, which is probably good. What you will do is easily break the bathroom scale if you're bouncing on it.
So,
Okay.
about the question before, on the thing, it says 71 centimeters.
Yeah, it has the answers wrong. As I said, I submitted an error thing because they have the answers wrong.
Okay.
They had the answer wrong for the part A, or the first one as well.
So it should be this number, right?
Yeah.
Okay.
I mean, I'm pretty sure they have it wrong. I tried to figure out how the answer could be anything different, and I couldn't.
So we find KE maximum.
Okay, that is one approach. There are many approaches to this one, and that's one of them. Okay, so that's one primary way of doing it. The other primary way of doing it is potential energy maximum.
Three.
Good.
So energy store is both kinetic and potential.
No, this one here is the calculation of the potential energy directly. This one here is kinetic energy. We know energy is equal to kinetic energy plus potential energy.
Mm-hmm.
So when potential energy equals 0, energy equals kinetic energy max, right? And when kinetic energy equals 0, energy equals potential energy max. So that means the total energy is equal to both the maximum kinetic and the maximum potential. So if we find the maximum kinetic, that should be the total, which should be the maximum potential. So the one in the red box is the direct calculation of what it asked.
Oh.
But using this logic, the first one was also a correct calculation to get you the maximum potential energy.
Okay.
Now, one thing that our calculation ignored is gravity, right? Because your gravitational potential energy is going to be part of your potential energy as well. And we only calculate the spring potential energy here. Why didn't we consider gravitational? Because actually, 85 times 9.8 times 0.002 is probably not insignificant compared to 3. Yeah, it's 1.66. So the change in gravitational potential energy would be 1.66 joules as you go through it. It's for that reason we usually do general physics problems. Just do it horizontally, then you don't have to worry about the gravity causing additional concerns. Okay, Brittany, are you down with this one?
Yes.
Shall we move on then?
Mm-hmm.
So going straight on to the next one.
Yes.
I also gave this one in the homework. I need to mix it up more. So we have a suspension bridge with an effective force constant of 1 times 10 to the 8th newtons per meter. How much energy is needed to make it oscillate with an amplitude of 0.1 meters? Now I said we should start with a picture, right?
Mhm.
What would you make for your picture here?
The bridge.
Bridge. With the force. Well, we don't know where the force is. Force constant.
Here's what I would do. Once again, a cartoon version. Here's the bridge,
Okay.
right? Is that what the bridge looks like? Clearly no. Clearly no. And it's moving up and down with some amplitude equals 0.100 meters. It has spring constant K is equal to 1.00 times 10 to the 8th newtons per meter. So I have the picture so I can think about what's going on. It's not the actual picture because the actual picture should have a bridge rather than a spring. But instead it behaves as with an effective spring constant, so I treated it like a spring. So now how much energy with this amplitude? So I'm looking for something that relates energy with amplitude. Not in this set of equations.
Mhm.
But it is right there.
Yeah.
Potential energy maximum is 1/2 Ka squared. And as we saw, the total energy is equal to the potential energy max. No, it's potential energy maximum. If you change it from A to X, then it's potential energy because X can change.
Mm.
So energy is equal to potential energy max is equal to 1/2 Ka squared. So we have K, we have A. This is
Oh,
getting trivial.
okay. Times 10 to the 6.
Should be times 10 to the 5th.
No, I just read it. Yeah.
And then we have the follow-up question. Or not the follow-up I was thinking it was going to be. As soldiers march across the bridge with a cadence equal to the bridge's natural frequency and impart 10 to the 4th joules, that's supposed to be 10 to the 4th, of energy each second, how long does it take for the bridge's oscillation to go from 0.1 meter to 0.5 meters in amplitude? So obviously our picture still works. What do we have for our idea here?
Like their concept?
Oscillation.
Relation between the spring of the bridge and soldiers? I don't know.
Well,
Oscillations.
we want to go from 1 meter in amplitude, or 0.1 meters to 0.5 meters in amplitude. So if the amplitude is changing, what else is changing?
Frequency.
The frequency isn't dependent on amplitude.
Yeah, energy.
The what?
Energy?
Okay, the energy is changing. So we're going to have potential energy initial, or not potential energy, just the total energy initial is equal to what we just calculated, 5.00 times 10 to the 5th joules. What's the energy final going to be?
5 times that.
Well, it's squared, so it's going to be 25 times that, actually.
Yeah, okay.
Now, I didn't do the calculation carefully. I did it in my head, so hopefully I didn't make a mistake. You would do it by saying 1/2 of 1.00 times 10 to the 8th newtons per meter times 0.500 meters quantity squared. What I got is very different from that. Yeah, I went the wrong way for criminy's sake. I went down 2 instead of up 2. That's a little embarrassing. Okay. Yeah, I have scientific notation. It takes me forever to count these things. 3, 6, 7. Good thing we double checked it, right? So, what's our change in energy?
One point two times 10 to the 7.
Yes. Now, coming back to the problem. This is getting into the realm of common sense, but you do have to know definitions. They told us we're imparting 1.0 times 10 to the 4th joules per second. What quantity has units of joules per second?
Power.
Power. That's right.
Good job.
So we have the power is equal to 1.00 times 10 to the 4th joules per second. So how does power relate to change in energy?
How does power relate to change in energy?
Yes.
It just has time as well.
Okay. The definition of power is the rate at which energy is converted.
Q over T.
So when
Q
it was
over T.
through heating, it was Q over T. But in general, it's the rate at which energy is converted. And so in general, power is the change in energy, right? The rate it's being converted.
Yeah, over the
So
T.
change in time.
Yeah.
And so what are we looking for?
Time. We're looking for time, so we switch. Change in energy divided by power.
Oh.
He's too excited, so good.
Oops. Okay. Go on to the next one. Okay, so physics. Awesome. Two identical springs are used to make a simple harmonic, or to make simple harmonic oscillators. A mass of 0.3 kilograms attached to one, while a mass of 0.7 is attached to the other. Which of the following statements is true? So I'm going to have so there's my two pictures. Which of the following statements is true? So we have a bunch of statements that I didn't copy because I wasn't thinking about it. Do both springs have the same frequency? I pulled out the two equations that relate this. Do they have the same frequency? Which the same as asking, do they have the same angular frequency?
No,
No. Why not?
because the mass different.
The mass is different. Okay, so we don't have that one. Next one. The spring with 0.3 kilogram mass attached will have a higher frequency. Well, just look at this. What makes the frequency bigger? A bigger mass or a smaller mass?
Small.
Okay, so that's small. I was thinking of mass, but the S's. Small mass produces. Hey, baby.
I'll just came by to say hi.
All right. Hi, baby. Bye. Small mass produces higher frequency. So the mass with 0.3 kilograms will have a higher frequency? Well, yeah, that's true. The other one, the mass with 0.7 will have a higher? Well, no, we just determined it wouldn't be true. The final line frequency of the spring will depend on the shape of the object attached. I don't see shape in those equations. Okay, next. I assume you want to go on.
Mm.
A 1/2 kilogram mass suspended from a spring oscillates with a period of 1.50 seconds. How much mass must be added to the object to change its period to 2 seconds? My pictures are looking fundamentally the same. So we have here period is equal to 1.50 seconds. And then we want to change this. So we have the same spring, but a different mass. Period is equal to 2.00 seconds. And they both have the same K.
So we use period equal 1 whole frequency. To find frequency, you need to find angular
frequency.
Angular frequency.
You're right. I'm just doing essentially what you said. So those are the two equations that go into the step that's not shown.
No. What is K? You just don't put
We don't know.
Oh, if we put M and T in first to find K, and then put K back again.
We can do that. Although we don't know what M is. Oh, we do know what M is. Bummer. The best way of solving this, that is the shortest, quickest way. When I say best, I mean the shortest and quickest. I don't mean like this is a technically better way. Is to say, well, period 1, well, let's do 2. Period 2 divided by period 1 is equal to 2 pi square root of m2 over k.
Divided by T. Everything cancel
Not everything, but a lot.
except M.
2 pi's cancel and k's cancel. So that's just the square root of m2 over m1. So what am I looking for?
M2.
Okay. So m2 over m1 is equal to t2 over t1 quantity squared, right? I squared both sides.
Mm-hmm.
And finally, m2 is equal to m1 times. Yes.
Oh, so here you have to flip it.
Hmm?
You know, from this because.
Well, yeah, because it's 1 over frequency.
Okay.
And so that, yeah.
Two. Mm. Point 1, 2. No, it's on.
Yeah, I was say that's a smaller number. I may not be the world's greatest mathematician. I know bigger from smaller. Okay, so I'm going to believe you on this one.
5 squared times.
Okay, I need to have my time with Russell now.
Okay.
Thank you.
Yes, ladies.
Thank you for recording.
You are welcome. You can thank the people who remind me.